For most people, these soap bubbles are just toys children play with. But in reality, they are the most spectacular, most beautiful masterpieces of nature. For reference, let me put a quote here. One of the Victorian scientists, Lord Kelvin, once said that blow a soap bubble and just observe it. You can study it all your life and draw one lesson after the other in physics. But what we can learn from this fragile skin made by the mixture of just soap and water? Well, technically, it can teach us a lot of lessons. And I'm not kidding. Soap films are helping us to solve some of the most toughest and complex problems in nature. Like as the planet Jupiter is a gas giant, and you can see these storms present in the Jupiter atmosphere. This is one of the examples how fluid can flow in a really complex way. Fluid flow is really beautiful, but it is also very difficult to study. The idea is that this exact process of fluid flow can also be created on the surface of a soap bubble. The soap bubble can help us because by tracking and following the colors on the surface of soap bubble, we can actually track how fluid is moving on the surface of the spherical soap bubble. That can give us a chance to study those systems that are either inaccessible or invisible. Just think for a moment how something that fragile and as thin as a single wavelength of light can tell us how nature works on the scale as large as our solar system. The soap bubble and soap film is in fact a mind blower. Well, this is one of the way how the soap bubbles can be used. But wait, the soap films are much more. Soap films are mathematical problem solvers. As you can see, they are in constant search of a geometrical perfection. Okay, that's great. So this was the pretty much theory how we can use soap bubbles in different areas of mathematics and in different area of science to study different complex problems and to actually solve them. How we can look up those. How we can study the storms present on the surface of Jupiter and how beautiful this fluid flow moment is, and we can replicate that moment in the laboratory here. We can play with it, we can track the colors on the soap film to study that complex behavior, otherwise that is inaccessible. And also, the fact that the soap bubble try to minimize its surface area, we can use it in mathematics to solve different problems and to really see the beauty present inside the soap film and soap bubble. So for that, here I have a demonstration, and I have here some bubble wands, and I have this soap solution, and I'll try some of the experiments related with soap bubbles, soap films, and the stuff like that, which is really amazing to see. And the fact that the soap film tries to minimize its surface area, the soap film is a natural surface. When I dip a bubble wand in this soap solution, and when I take it out, there will be a film established by the intermolecular forces of water. In fact, by the surface tension, a lot of these different forces play a huge role in making the surface film, the soap film actually. So there are many number of ways we can study these soap films, and uh, the fact that the soap film has colors and it is really thin surface, and it always try to minimize its surface. These are really cool things to look at, and these are really beautiful in fact. For the very first experiment, I will blow a soap bubble with this. This is an acrylic tube, and I'll use it as a bubble wand to blow a soap bubble. So let's see. Okay, this is the very first experiment. So you can see that this is a really nice spherical shape. When I blow a soap bubble, this is a really spherical shape. It is the same way that you blow up a balloon. That membrane stretches and pushes all of those elastic molecules of rubber and put it in a really nice spherical shape. So that is the same way we can blow a spherical soap bubble with this tube. The sphere retain its shape because the pressure inside the bubble and the pressure outside the bubble is the same. So the soap bubble is somehow retaining its spherical shape, the perfect sphere. We can say that this is a perfect sphere occur in nature because the soap film try to, it try its best to retain a spherical shape. So now I'll dip this circular ring in this soap solution. First of all, we see that this is a pretty strong film, and it moves up and down really vigorously, and it is quite stretchy. And the hydrogen bonding present between the molecules and the surface tension make it happen to achieve this strong effect, this strong thin film. Look at this. This is really nice. See how amazing, how stretchy this film actually is. The soap film always try to retain a spherical shape whenever it is not attached with a specific wireframe or a wand. So it try to retain that spherical shape because that is the least surface it can get. See this. This is really amazing. See this. We can always try to experiment with different things with different wands. So here I have a triangular wand, and now I'll try to make that a spherical shape, that spherical blob of the soap film with this triangular. So no matter what is the shape of that wand, the resulting bubble will be spherical because this is the theory. The soap bubble always try to retain a minimalistic surface. So now I'll dip this triangular wireframe in this soap solution, and see, it always try to get a spherical shape. It always tries to make a sphere whenever it detaches the wireframe, the triangular wireframe, for instance. So here I have a square wireframe. I have a lot of 2D shapes. So I try my best to replicate every 2D surface. I don't have polygons, but okay. See this. So I have tried these 3 shapes and I got a sphere at the end. So those are 3 2D shapes. Here's a triangle, here's a circle, and here's a square. And the end product, the film which try to detach from this wire mesh, from this wand, is actually a sphere. So those are the three 2D wands I try to look upon, and I've tried to study it. And the end product will always spherical. And the bubble which try to detach from these three rectangular wands, from these 2D wands, will always be spherical. In chemistry, we learn about the intermolecular forces and how the hydrogen bonding present in the water affects the behavior of the water. So these demonstrations can be, can be performed in this topic, relating the intermolecular forces with the strength of soap bubbles. The soap bubble and the film get its strength from those intermolecular forces. So here it is a really large, this is a relatively large wand, and when I dip it in the soap solution, I'll try to really carefully manage to get it out, because it is really fragile and I'm not having a success with it. This is a really nice flat surface. I can feel it. I can feel the inertia. This is amazing. You can see this surface. It is acting like a trampoline. This is a gigantic surface. You know how it moves up and down. This is the beauty. And I'll make a soap bubble on it and try to play with it. Okay. It passed straight through. Look at this, how stretchable this membrane is. Oh, it is really difficult to maintain all these things together. So here I'll get a film and I blow a soap bubble. It actually catches on the surface. Look at this, look at this, look at this, look at this, look at this. I can play with it. Okay, here it is, here it is. Oh. This thing is really cool. I can play with it literally for hours and hours. I urge you to, build these things by yourself and play with it. It is a lot of fun. Look at this, look at this. Well, this is a classic. So how can I join all of those points? All of those points. This curve is a collection of points. So how can I join all of those points? The point, that imaginary point present on this wire with this wire with this. So how can I join all of those points with the least amount of surface possible, with the least amount of energy? The nature, the principle of nature is that all of the systems around us are trying to minimize their energy. So how can I join all of those points with a surface that has a least amount of energy, least amount of material, and least amount of surface, for instance? So the soap film can give me answer to all of these questions in an instant. Here is that surface. This surface has the minimum area, the minimum amount of material is being used to make that surface. Minimum amount of soap film is used to make that surface. And this is an optimal pathway. This is an optimal solution to that surface. This is optimal mathematical solution. We call that singularities. So these are the theoretical sort of mathematical idea that how, you know, if we can solve this surface, if we can solve this surface without a computer, you know, this is a work for the computer, for the supercomputer, for instance. We try to solve these problems with a computer for all those mathematical calculations. So the SOAP film can answer all of those questions. What is the optimal pathway? What is the optimal solution to a problem? And this is also beautiful to see. So now returning to 3D. Now those were all of the 2D objects, 2D shapes, and this is a 3D shape. Now how I can join all of those points from this side with this side optimally is the key here. You know, I can try maximum, I can try infinitesimally many methods to join all of those points. I can join them with a straight line so that it will look like a cube. And what I can do, what else I can do? I can try many things, but maybe it can make a V shape. It can make a V shape like this. So how it will join all of those points? So let's see. Here it is. It is really beautiful shape. See this. This curve. It will always take that curve. This is the optimal solution to this kind of problem. This is the optimal pathway to join all of those points together. So this is really interesting. Let me try. This is a cube. This is a three-dimensional object. You can see that all of these sides are equal, and I dip it in the SOAP solution, and there we go. A really interesting, really beautiful pattern emerges. So this is the minimal surface that requires. This is the only surface which can join all of those sides of the cubes together with the minimum SOAP solution, with the minimum amount of SOAP solution, with the minimum surface area possible, with the least energy possible. Every time I put this wand, this framework in this soap bubble solution, I'll get the same result. There's a little, oh, I broke it. So the next demonstration will be with this. This is a bubble wand, and what I have here, I have a wire mesh, a piece of wire, which is being made like this. So I have a piece of thread here joining those 2 points, and all of those points are actively linked with this handle. But with those 2 points, I have connected a piece of thread, and this is a loose connection. This string is really, loosely connected between those 2 points. So I will dip this arrangement in the SOAP solution. Look at this. This actually tells us the effect, how stretchable this film actually is, how stretchable this film is. So I'll try to pull this whole surface away from that edge, and I can feel a force. I can actively feel a force. This thing is quite active, and this thing is pulling opposite. Whenever I try to, pull it in this direction, the film actually apply a force in the opposite direction to, try to represent that this is in fact a stretchable thing, and there is plenty of force required to pull this surface tension. The pulling effect of this surface is quite strong. So with this simple experiment, we can experience those intermolecular forces by ourselves, and we can demonstrate them in the classroom so that the students can actually see that it is actually a force, and it is actually a feelable force. I can feel it. I can experience it. So this is quite stretchable, and when I leave that thread, it will force back to its original shape. Here I have another one. So these are two rods, the same wire from this. So these are two rods, and these are connected by two threads like this. So I dip it in the soap solution, and what we have observed that the thread is also curved inwards, representing that there is actually a force. You can see in the camera that this film is actually reflecting the light from the studio light in the camera there. So this is also an effect of the soap film, that it can reflect, and it can show us some amazing colorful artistic effects of light. That the film is really thin, that it is almost a single wavelength of light thick, which is unbelievable with this simple kind of equipment, that we can cutting edge sort of thickness with this kind of simple apparatus, which is also really amazing thing. This demonstration involves this loop of thread, this loop here, and what I'll do now, I will make a film on this circular wire, on this circular wand, and I will try to, this is a really difficult experiment. I alarm you. The surface film, the film break every time. So let's see how this goes. So I have here this film, and I will place this loop of thread on this film like this, and then I break it. Internally. You can see that how effectively this the round shape, the circle is put into action. The thread takes the circular shape instantly. That circle represents that there is a evenly distributed force from all the directions from the periphery of this wire. Well, these are the beautiful lessons that nature has for us, and it's our duty to explore all of this hidden characteristics, hidden beauty inside those things. So with these experiments, these kind of cool demonstrations, those represent a really beautiful insight of the science and the beauty of the world around us, the enchantment it has for us to explore, to know more about the world, and to experiment with those things. And I thank you for listening.